A good call on that. Okay. So I'll just jump into the properties then, and yes, I'll speak to Kyle's point here momentarily. Okay. So let's make some remarks on the Poisson kernel. Okay. So first of all, if I set R equal to 0, so let's just look at right at R equals 0, we have U of 0 phi, right? 1 over 2 pi integral from 0 up to 2 pi. But if let me just flip back here, right? If I plug in 0 here, right, I get a 0 here, I get a 0 here, I get a 0 here, I get an a squared on the bottom and a squared on the top, right? So those cancel out. And I just have an average, right, of my boundary, right? What is that I've just discovered that I've satisfied? It's a property that involves the average value.
Mean value property.
Yes. All right. So the mean value property, right? Well, that's good because it better satisfy that because it's supposed to be a harmonic function, but it's a good sanity check, right? And I would say anytime, either in this course or anywhere, you should always do sanity checks on your solutions to make sure that they satisfy all the properties that they should, okay? The other thing, if I set f just equal to 1, what would you guess is going to happen to U? If the boundary is a constant,
U will be a constant.
U should just be a constant. And that is by the something principle.
Strong max and min principles.
Yeah. Strong, yeah, weak would work too. So in this case, U equals 1, right? And now we know that by the min maximum principle, right? If you look back here, right, I mean, it's not immediately obvious that will work out. You have to do kind of a thorny integral here, but we can just go ahead and apply the why did I write max min principle? Min max principle, max principle. Okay. So what does that tell us? Well, it actually tells us something interesting, which is that the integral from 0 to 2 pi of p of r over a psi, the psi is equal to 1. Okay. So that means the Poisson kernel, okay, is normalized, right? Just like our fundamental solution was for the heat equation. So there's some parallels here, but not everything works the same. Also, the Poisson kernel is singular, okay, at r equals a. So essentially, the limit as r phi goes to a, say, theta, so u of r phi, that's going to be equal to f of theta. Okay. So we recover what we should, right? When we take the limit back to the boundary data, just like we did in the heat equation, we should recover that boundary condition. So that must mean that the Poisson kernel is behaving like a delta distribution on the boundary, right? And so you can see here, right, this is going to go to 0 in that case, right? This, right, on the boundary here is going to be, yeah, it's a little bit clear, right, how that behaves, and we're not going to go through that proof, but it does recover the boundary data as we take the radius to the outermost boundary, okay? And then to Kyle's point, the geometric interpretation of the Poisson kernel is, let's say x, right, we define that as a vector from the origin, okay, to some point r phi. And we define x prime, okay, as some vector from the origin to a phi prime, okay? Then what we have in that case is we can draw this sort of triangle, right? So here's my x here, okay? I'll label this radius as r here, and then I'll draw another vector here. We'll call that x prime, and that's going to be living on the boundary here, right? A phi prime. And then this is my phi here. So then the intermediate angle here is phi minus phi prime, okay? This vector has length a here, and we complete the triangle here. And essentially the law of cosines, so like exactly what you're saying there, Kyle, is x minus x prime is equal to r squared plus a squared minus 2ar cosine of phi minus phi prime. Okay, so if you had this sort of geometric intuition, right, you can get this rule this way. However, right, a squared minus r squared equals x prime squared minus x squared. This is actually true for any dimension, so not just for R2, okay? So you can't work things out quite as cleanly using separation of variables for any set of dimensions. But in general, this solution, right, u of x, right, I'll just sort of write it in Cartesian coordinates for an arbitrary dimension. We just take the average over the boundary of this quantity here, x prime squared minus x squared divided by x prime minus x squared, u of x prime here, okay? ds, so now an integral over that boundary, okay? And this is true as long as x is less than a, and it's true in a ball on a disk, basically. So let me write, you know, a ball on a disk with radius a, okay, that lives in Rn. Okay. So this kind of law, this geometric interpretation carries forward to any n dimensions. Okay. Now, the Poisson kernel, right? Sorry, did everybody finish that up here? Can I move on? Okay. All right. So the Poisson kernel, right, is an example of what's called a Green's function, okay? And in general, Green's functions, okay, can be convolved, okay, with boundary and or forcing conditions, okay, to obtain solutions to BVPs and IBVPs, okay? So initial boundary value problems, just like the heat equation, right? And boundary value problems, right? This is like for Laplace and Poisson's equation. Okay, and we have the Poisson kernel. Okay, and I'll say et cetera because there's some modifications that we have to make in the case of Poisson's equation. Okay, so it seems like, okay, great. What I'd like to do is for any particular boundary value problem, initial boundary value problem, it would be great if I could identify these Green's functions, and then that would allow me to solve any
Can no one else hear him?
No, I think he's gone.
No, yeah.
Yes.
Yeah, he's just gone.
no. Somebody have a question?
We didn't hear the last like 35 seconds of what you said.
Okay. Oh, bad connection? Okay. Yeah, so the yeah, I missed that, a bad connection. So essentially the so that a Green's function is extremely powerful because you can for any particular linear operator, as long as you find the Green's function for that linear operator, then you can adapt the Green's function to different boundaries using techniques, one of which is called the method of images, okay? For sort of, you know, shaping corrections to the Green's function that are adapted to that particular boundary, okay? And so in the next couple weeks, that's what we're going to look at, is this general approach of Green's functions. We're going to apply it mainly to the Laplace and the Poisson equation, but it's relevant to wave, heat equation, lots of different linear partial differential equations. Okay. So we're kind of done with that, the main chapter on Laplace's equation, and we're moving now into Green's functions in general. Okay, so so let me start this section on Green's functions now. And we'll see how far we get. So the idea here is that we'd like to develop a method, okay, to solve partial differential equations, okay, by integrating a fundamental solution against inhomogeneities, okay? That's really bad writing, okay. Inhomogeneities, okay? So for example, right, take Poisson's equation, okay? If I take Poisson's equation, I'd like a way to convolve against that inhomogeneity F, okay? And in fact, in general, on Rn, this has a solution, okay? U of x is equal to Well, I know it, right? It's my fundamental solution to Laplace's equation, just convolved against my inhomogeneity there, okay? But the big step in terms of making these usable Green's functions, okay, is incorporating boundary conditions. Can we also incorporate boundary conditions, okay? So let's say I poke holes in my domain. I cut the domain off. I only want to deal with a half plane. I only want to deal with a quarter plane. I want to deal with a disk, okay? How do I manage that? And some of it comes down to a problem of conformal mapping, okay? And other parts of it come down to sort of geometric understanding of how to sort of reflect points from